I'm defending my master's thesis today, and this is about resolving the scalability issues that we faced in Orbit NodeHandler when we had to make the NodeHandler work. That is when the Orbit made the transition from a 64 node grid to a 400 node grid. The difficulties we faced in getting the NodeHandler to work and how we overcame those difficulties constitutes this thesis. This is my plan of discussion. The introduction where I'll discuss what was the problem, what was done, what's the scope of this thesis. Design overview is about the architecture of the new NodeHandler, the NodeHandler that works successfully on the big grid. When I say work successfully, I mean that the NodeHandler is able to image 400 nodes successfully. So in node imaging, I'll discuss what node imaging is and how it's done. The entire investigation work was done in 3 phases: phase 1, phase 2, and phase 3. So in this phase, in these 3, I'll discuss what is unique about each phase, what was done at each phase.
Hey, Marco.
Hello, wait.
Yep, so we started a teeny bit without you. She's introduced herself, and she's now going through the overview slide.
Okay, so Saswati, if you could just say next slide every time you're switching the slides, then I can follow along on my slides here.
Okay, sure.
All right, can you hear her? Marco, can you hear her? Go ahead.
Can you hear me?
Yes.
Okay.
Okay.
I'm in the second slide in overview.
Okay.
So in overview, I'm saying that the entire investigation work was done in 3 phases: phase 1, phase 2, and phase 3. So in each phase, I'll be discussing what is unique to that phase, what was done at each phase, and at the end of the investigation work, what was the conclusion. Yeah. Actually, I need to change this also.
It's fine. You'll be able to hear her. Don't worry.
Now, from the entire investigation work, important lessons were drawn. This is what I'll be discussing in lessons learned, and conclusion is about the overall conclusion of the entire investigative process. Next slide, please. Next slide, please. We all know what Orbit is. We are associated with Orbit. NodeHandler is the central experiment controller in Orbit. It's the software that accepts the script from the user, steps through the script, sends commands to the NodeAgents, keeps track of the status of the experiment, and at the end of the experiment, it determines whether the experiment has been successful or not. The NodeAgent is the component equivalent of the NodeHandler that resides in each node. Each node has a single NodeAgent, and what the NodeAgent does, it listens to the NodeHandler. It can start and run applications. It can pass dynamic parameters dynamically to the applications, and it reports the status to the NodeHandler. Now, when the transition was made to the big grid, it was found that the NodeHandler version, which was 3.6.4, which worked flawlessly on the 64 node grid, didn't work on the big grid. So work was taken up to get it to work, and the entire work done constitutes the basis of this thesis. The scope of this thesis is twofold. Firstly, what was the problems were identified. Each and every problem was isolated, its causes was determined, and since this grid was new, there was never a 400 node grid, there were some unique grid requirements too. Those were identified, and once these were identified, in the second stage, the NodeHandler was re-architected. A new NodeHandler was developed, which is scalable and which works on the big grid. Next slide, please. This is the design overview of the new NodeHandler. The NodeHandler of version 3.6.4 had 3 components. First is the request handler. It's a multi-threaded process, and it had three main components, which were all each components worked as part of a thread. The main was the request handler, which implemented the core NodeHandler functionality. The second was the communication layer, which controlled all communication between the NodeHandler and the NodeAgents. And the third was the web server. The web server maintained an XML data structure which was visible to the users. Now, in the new design, what was done is, another factor that was taken into consideration was the limitations of the implementation language Ruby. So in the new architecture, these three components were separated. The request handler, which performs the core NodeHandler functionality, now was transformed into a separate process, the NH process, which is shown here as NH. What this does is, this waits on a message queue, retrieves messages from the queue, processes them, and sends it to the NodeAgents. To send messages to the NodeAgents, it opens up 4 multicasting sockets. Previously, it used to open up only 2 sockets, one socket for the entire NodeHandler to NodeAgent communication, and another multicasting socket for the NodeAgent to NodeHandler communication. But now from NodeHandler to NodeAgent, there would be 4 multicasting sockets. And the entire 400 NodeAgents were divided into 4 groups based on their IP addresses. Like the NodeHandlers, each group size was 100 NodeAgents. So there were 4 NodeAgent groups. And each NodeAgent, each node on booting up, using its IP address, identified the multicasting socket to which it should bind and get messages from. Next, the communication layer was re-architected. The communication layer, which was first turned into a single Ruby process, but because of Ruby implementations, it was found that even a single client process dedicated to communication handling between the NodeAgent and the NodeHandler couldn't handle more than 200 nodes. So what was done is, similar to the previous case, the NodeAgents were divided into groups of 100, and there were 4 Ruby clients assigned to each NodeAgent group. Now the NodeAgents send the messages to the client process. The client process does some initial filtering on the messages received to reduce the workload on this NodeHandler process, and it writes the messages to the message. All these write the messages to a common message queue. And the NodeHandler waits on this message queue and it retrieves the messages. The third component was the web server. It was deemed unnecessary at this stage, and so it was removed. So as you see, this is an architecture that is a bit limited because it doesn't have the web service facilities. And another observation that was made was in investigation phase 3, which is like the phase in which all robustness and optimization was done. It was found that even with this architecture and Ruby as the language, the maximum processing capability seems to have nearly been reached. So for nodes with bigger grids, for grids with bigger nodes, this architecture might not be sufficient. So where is the message queue? This is the message queue.
Yeah, where is it? Is it part of the NodeHandler?
See, it's now separate processes. You have the NodeHandler process, which is the core functionality. And before we had another thread that was the communication layer. So you can say that these 4 processes constitute the communication layer, the aspect from the NodeAgent to the NodeHandler. Okay. And previously what this used to do is, this used to say the communication, whatever message was received from the NodeAgents, the communication layer is to receive it on a socket, and the NodeHandler is to wait on that socket and receive that multicasting socket. But now what happens is, these have their own sockets. These are receiving the messages, filtering to reduce the number of messages that the NodeHandler gets, and then it writes these messages into a common message queue.
What does write it mean? I'm not able to picture where is so is this message queue in the memory in the NodeAgent or in the NodeHandler or in the console?
Where is this data structure stored?
Okay. This data structure is stored, this is a Unix message queue, IPC. And this is stored where the NodeHandler server is running. Okay. These are the 4 client processes. Like previously, what was there? A single process, the NodeHandler is running on the server. Now it's the same thing. These all constitute the previous NodeHandler. It's only that there are 3 processes running on the server where there are multiple processes running on the server where previously there was 1 running on the server.
So, Saswati, to answer the question, is NodeHandler on a different server? Is NodeHandler running on a different server?
No, these are only the NodeAgents are running on the nodes. The rest all are running on the same server.
Oh yeah, that's what was.
Here. See, here what happens is the NodeAgent is on the node. It sends the message which is received by a socket, multicasting socket here. This is running on the server. So this writes it to a Unix message queue.
So all this is only that NodeAgent group cloud which you have drawn, those are
In the nodes.
real nodes.
Huh.
Everything else is in the
On the
server.
server.
Here.
So the server runs this.
Okay, all
NodeHandler
these different
process.
entities as separate processes.
Here. It's like when you go to internal 4 and you type NodeHandler -t, you will be doing the same thing. Because where it was previously NodeHandler -t, this now has these clients, but these are invisible to you. You don't have to worry about those. This one will internally take care of forking this, and then at the end it will clear this up. So keeping in view the limitations, this is the future work for a completely scalable design. Where as you see, this is the same as before, which was the experimental version. But here what happens is, when the number of nodes is large, we can have multiple NodeHandler processes. These NodeHandler processes can communicate with, if they are on the same server, they can communicate using a shared memory. So each NodeHandler will handle a subset of the nodes, and the status, the progress of the experiment, everything will be written to this shared memory. And we can have a front-end web server. In the Ganglia system has a similar web server that deals with XML data. But XML data needs a lot of processing. So in Ganglia what happens is there's a dedicated powerful server dedicated only to the XML related functionality. So here we might not need something so powerful. So this can be a separate process, though a process separately dedicated to the XML functionality.
So what's the benefit of having multiple NodeHandler processes?
See, in the previous one, I found that this has, like with the existing Ruby, this has almost nearly reached its limit when it processes 400 nodes. So if there's a bigger grid which has 800 nodes, the single NodeHandler process might not be able to support it.
So the limitation is with the
Ruby language. I would say that we need to explore, which I will be putting as part of the conclusion, that we need to explore something in other language like C, C++, something. Because a single client, this is a client which is dedicated only to receiving messages from the NodeAgents and writing it, and does a preliminary filtering. Like every 5th heartbeat message, find it out for a node and send it to the message queue instead of everyone. It can support more than 200 messages coming from the node. If there are more 200, it's handling 200 nodes.
So what if you have more clients?
Yeah, we can have more clients, but then this might reach the limitation processing limit. So this is a suggested architecture for a complete scalable architecture if we have bigger grids, in case in future we want to extend this 400 to maybe 1000 node grid, or things like that. Next slide please. It's the slide where I am explaining node imaging process flow. Now what is node imaging? Node imaging means installing the OS on the node. this is a very critical orbit functionality where the user is allowed to download the OS and other software components that are part of his experiment to the node, so that the user can then use this to perform his experiments. This node imaging is done using a specialized script. The node handler receives this script. Once it receives the script, from the script it identifies which nodes, what's the entire set of nodes on which imaging has to be done. What it does is it switches on the nodes. And once it issues a power on command, after that it goes on sending hello messages periodically to those nodes for which it was issued a power on command. The nodes on their part wake up and they boot off. They have two options to boot. One is they can boot off the image that is present in the local disk, which is the default one. But in case of imaging, we want the NodeAgents to boot off the PXE image, the specified PXE image. And the node handler will keep a check whether a NodeAgent has booted off its local image or the PXE image. Now, once the node boots up, what it does is it sends a check-in message to the node handler. The node handler checks the message, and in the message is specified from which image it has used to boot up. If there's a mismatch, what the node handler will do is it will send a reset to the NodeAgent and say, boot up again, you have booted up the wrong image, the wrong OS image. And these PXE images have a NodeAgent. Once the node boots up, the NodeAgent starts. Now, if the node has booted off the correct image, then the node handler keeps on checking. When the node boots off the correct message, boots off correctly, it sends a check-in message to the node handler. Now what the node handler does is it verifies its correctness and sends an LS message back to the NodeAgent. Now the NodeAgent receives this.
Actually offload this checking capability to the NodeAgent instead of running it on NodeHandler.
Offload means?
I mean, why can't the NodeAgent check whether the image is correct or not? So it has.
That's a limitation in the NodeAgent hardware. I don't know why this is.
So it doesn't have that capability.
Yeah, there's a switch in the NodeAgent software. Like sometimes based on that switch, it should boot off the PXE image, but sometimes the switch is missed. This is internal to the NodeAgent other software, which is not like your NodeAgent or NodeHandler software.
Okay.
So once it receives the LS, the NodeAgent receives an LS message from the NodeHandler. Then from then onwards, it periodically keeps on sending heartbeat messages to the NodeHandler. The purpose of the heartbeat messages is to inform the NodeHandler that the NodeAgent is up and that it's in communication with the NodeHandler. Now, once the NodeHandler decides that all the nodes are booted up correctly, it starts the load image procedure. The load image procedure is it starts the Frisbee server, which is a multicast server, and then sends a load image message to each of the NodeAgents. Once the NodeAgents receive the load image message, the Frisbee client is started up, and which then starts writing the image to the disk. And also the NodeAgents periodically keep on reporting the status to the node handler. What's the status? 10% finished, 20% finished. Now, at the end of the imaging, if everything is successful, the NodeAgent sends a message, an app event message with the keywords done.ok. Once the node handler gets this, it realizes that the node has finished imaging. It waits for all the nodes to finish imaging, and once all the nodes are finished, it switches off the nodes, it kills the Frisbee, and it removes the PXE links which the NodeAgent had used to boot off of the PXE. So this, in short, is the entire imaging process. Now this is the next slide please, the imaging script slide. Now this is the specialized script that is used for imaging, this is the script for 3.6.4. I've optimized the script for this, the new node handler, and I'll be discussing it later. In this script, first, as you see, the experiment name is defined. Then the property in this, the range of nodes to image, which nodes to be imaged are defined, and this is the image name. the image that is to be written to the disk. The def nodes here defines which orbit image is to be created by the PXE and which is to be used by the NodeAgents to boot off from. These three constitute your defining the parameters of this experiment. Now what happens is, after all and every call is made, what this every call does is, it starts a new thread that wakes up every 10 seconds and it checks that whether the load image has been started, process has been started. If it started, it keeps on checking the progress of the imaging progress. The next command, the next slide please. The next command is when all up. This again starts another additional thread. What this does is, it checks whether all the nodes are booted off correctly, and then it starts the load image procedure. And once this is done, it sleeps. In step 6.2, when all is called, this again starts another thread. What it does is, here it periodically checks whether the nodes have sent the done.ok message. And for that, as you see here from this string, it parses the XML data structure. And if it receives that, and it checks whether the done.ok message has been received, and once all of them have report done.ok, it starts the shutdown process. In step 7.2, the NodeHandler web server is mounted. This again results in another additional thread. So as you see, from an user script, we can add more threads, additional threads to the NodeHandler process, which basically changes the architecture of the NodeHandler. The next slide please. Huh? This is 3.6.4. It was the old one which worked. Now the investigation was started using 3 phases. In phase 1, the basic investigation work where no architectural changes were planned. The main focus was to identify the problems. What are the problems? Isolate the problems, find the root cause of the problems, and we could see that we could modify the code and get it to work. Now problems were divided into several categories. One is the experiment termination failure problem. It was found that there were cases where we start the imaging, but the nodes never complete, where the NodeHandler never completes its imaging. So there were found that there were several problems which could be grouped under this category. Case 1 is the progress status discrepancy subproblem. In this case, what is happening is the NodeHandler and NodeAgent both maintain a detailed log file. So what I did is, when I encountered a problem, I analyzed the log file to find out why this was happening. In this you see that we are trying to image 100 nodes. Now when we image 100 nodes, the progress status tells us this is the progress, the least progress made by a node, this is the most progress made by a node, and this is the average of all the nodes. In this case you will see that the second node in row 20, this is at 0, which means that this hasn't even started imaging. But again, when you analyze the log messages, you will find that I found that there was a message which said that this same node, row 20, second node, had progressed to 90%. But here it says that it hasn't even started imaging.
Are those from the same logs, or they are from?
Yeah.
So this log was maintained by NodeAgent or NodeHandler?
This is a NodeHandler log. Next slide please. Case 2. Other problem is the missing messages subproblem. As I said earlier that what the nodes do is, the NodeAgents periodically report the status, 10%, 20%. After a node has reported 90% complete, it sends an app event message with done.ok status in that. After the done.ok, the sequential order of messages sent, it sends another app event message which says that it wrote this many bytes, and that after it's completed, it's left the team. What was happening was this done.ok message was missed. It wasn't there in the NodeHandler log. And since it wasn't there in the NodeHandler log, the NodeHandler kept sending repeated retries, that it was sending retry commands to the NodeAgent saying that send this message. But this message never appeared in the log file. So what was happening, since this done.ok was not there, so the NodeHandler thought that imaging has not been completed for this node. The third problem was the next slide please. The third problem was the queue buildup. As I said, the NodeHandler is a multi-threaded process where one thread receives messages being sent sits on a multicast socket, receives messages from the NodeAgents and puts it on an internal queue. Another thread reads from that queue and processes the messages. This thread is the request handler thread. What was found that the messages that are getting received from the NodeAgent and inserted into the queue, that particular queue was increasing in size and the size never decreased. Like here you see 1800 messages, more than 1800 messages are already in the queue. This meant that the request handler thread which was retrieving and processing these messages was very slow. And so a calculation was done and I found that for 11 messages that were being pushed into the queue, only 3 were getting popped and processed. The next category that I had was the communication breakdown, which is a breakdown of communication between the NodeHandler and the NodeAgent. The first, the next slide please. The first is the lost handler subproblem. What happens is, once the NodeHandler comes up and the NodeAgent says that it has also booted up successfully, the NodeHandler keeps on periodically sending a message, a ping message sort of to the NodeAgent. The NodeAgent has a timeout parameter internal to it. It receives this message and it checks whether within this timeout interval the NodeHandler has sent any messages to it or not. If it isn't, then it decides that it has lost contact with the NodeHandler, and that's when it generates an error message, NodeHandler lost to us. So in this case what was happening is, first a single node sent the lost handler error message, but with the progress of time it was found that more and more nodes were sending this message. So the log file was for the NodeHandler was analyzed, and it was found that no message was being sent that particular ping message was not getting sent to the NodeAgent. The NodeHandler has a dedicated thread to send this message to the NodeAgent. This thread was not getting scheduled or the thread had crashed. Similarly, for the NodeAgent which said that it had lost this contact, I went to the log file for this NodeAgent. So this log file also said that there was no record of any message getting received from the NodeHandler.
So this step is used to identify the reason for the first 3 cases, or this is different?
This shows that there has been a communication breakdown between the NodeHandler and the NodeAgent.
This is a different problem.
This is a different category of problem. Like this was the problem. These three problems under these showed that for 3 separate cases the experiment was not terminating. This was like that the messages being sent by the NodeHandler was missing, and that seems to be a communication breakdown.
Okay.
The next case was the packet loss subproblem. What happened is, it was observed that the NodeHandler, and most of the problems we faced were from the NodeAgent to NodeHandler communication path. The NodeHandler to NodeAgent communication path worked mainly. So in this it was observed that the NodeHandler didn't receive messages from the NodeAgents. So a TCP dump utility was started on the NodeHandler, and it captured, for a particular NodeAgent, it captured 130 packets. Then I looked into the NodeHandler log file, and it said that there were just 12 messages from this particular NodeAgent. I went to the NodeAgent log file, and there were 130 messages sent to the NodeHandler. So this, in a sense, exonerates the underlying socket layer and pinpoints that the communication problem is internal to the NodeHandler. So all this I was doing to narrow down the scope, like where exactly the error is. First it can be anywhere, and then I narrow down the scope to pinpoint exactly where the problems were occurring. The second was the repeated node reset problem. As I said earlier, when a node boots up, it sends a check-in message. In this case, what was happening was the node was booting up correctly, it was sending the check-in message, but the node handler was not receiving this message. And so the node handler was repeatedly issuing resets, and the node repeatedly kept booting up. The next slide, please. Now, as we say, the problem causes, first is the communication layer, which is very apparent. Now, TCP dump helped us isolate that it's not the underlying socket layer, but the communication layer in the node handler, which had the which was the cause of the problem. Initially, we had all thought that the multicast sockets, the buffer size associated with the multicast socket was small. So maybe a buffer overflow was causing packet loss, but using TCP dump, we realized that that's not the case. Similarly, the node handler process is multi-threaded, and in imaging, when we go to image, there are 9 threads which are accessing the shared data structure. An error message came up which showed that a shared data structure, which is a hash data structure, it had been modified by a thread while it was being iterated upon by another thread. And worse is that multiple threads was used to access the same data structures, read and write from the same data structures. Next slide, please. So in multi-threading, it was that the process status discrepancy subproblem, where we saw that the status is 0, but the node handler log file also said that 90% progress has been reported. This can be caused by a race condition, where 2 threads were trying to access the data structure, and so the latest status was not updated. Similarly, queue buildup shows that the threads that processed on this was taking a large processing time. Similar is the case with the missing message subproblem. Also, it was possible that all these problems were being a combination of both the communication layer and the multi-threading problems. And another thing is that in the 3.6.4 node handler code, though multi-threading had been used, there was no explicit multi-threading support in the code. Like shared variable serialization was absent. Critical section serialization access was not restricted. The code relied on coarse grain Ruby locking, but that seemed to break down under cases of heavy load. So next slide, please, where I am describing the code enhancements. So I tried to enhance the code. The first is thread prioritization. Since all the 9 threads have equal priority, what I did was I identified threads. Like there were 3 types of threads. There were 2 types of threads mainly. The first is the threads that keep on continuously working. The second is those threads that sleep, wake up, check, and sleep. Now, isolated the threads that keep on continuously working, and I assigned a higher priority to those threads, and a higher priority of 1, and the remaining threads at a priority of 0. Once I did that, I saw massive thread starvation. The rest of the threads were getting starved, and the lost handler problem, where the dedicated thread to send the ping message was not getting scheduled. So the lost handler problem became very severe. Similarly, again, I tried a 3-level priority where I assigned the top most processing threads a priority of 2, the web server thread a priority of 1, and the remaining threads a priority of 0. But the thread starvation problem seemed to increase, and so I had to abandon this approach. The next what I tried is I tried to serialize the shared variables. I identified the shared variables, and I implemented mutual exclusion.
So if you give higher priority to those threads who only wake up after some time, does that solve the problem?
No, it didn't. These threads are not operating system threads, these are Ruby threads, and they are much slower.
They are?
they are much slower than operating system threads.
They're Ruby threads.
These are internal Ruby threads, not operating system
So
threads.
I don't understand. Usually, if you have two sets of threads, right?
Yeah.
One continuously running, the other it's like periodic.
Yes.
You usually give higher priority to the periodic threads because they will go to sleep anyway. When they are asleep, you can schedule these continuous threads. If you give higher priority to these continuous threads, apparently you are not solving the problem, right? But
Yes.
even you give higher priority to these periodic threads, you are not solving the problem.
In the 3-level priority scheme, I had given a higher priority to the thread, the dedicated thread that sends a ping message. But what happens is, if I give a higher priority to any thread, it slows down the request handler thread. And in NodeHandler, that does 90% of the processing. I tried all thread combinations when I assigned these multiple priority schemes.
What's the main reason why it's not working? I'm just curious because
The main reason at this, when I removed the priorities, was when I assigned the unequal priorities, was that there seem to be some threads that never get scheduled.
why?
The one problem, one possibility might that these are Ruby threads and they have a fixed time slice. So they wake up at a fixed time, and within what one thread was doing is, even if it's round robin scheduling, it was only after the processing thread, request handler thread finishes, then it allows another thread to schedule.
Okay.
So if the thread is supposed to be periodically waking up after 6 seconds, it wakes up after 6 seconds, the request handler thread doesn't assign it resources, so it again slips off. So a thread that was supposed to wake up every 6 seconds wakes up after 21 seconds. Is assigned resources after 21 seconds.
Okay, so it's really poorly designed.
Yes, yes. Now, I implemented serialization of shared variables, and this further degraded performance. So I had to abandon that approach also. Next I concentrated my efforts on the communication layer. The most of the problems, as I mentioned earlier, was from the NodeAgent to NodeHandler communication path. What happens is, in 3.6.4, the NodeHandler opens up 2 multicast sockets. One socket is used for sending messages to all the NodeAgents, which is pure and which is what multicasting is supposed to be. But in the other socket, a single multicast socket is used to receive messages from all the NodeAgents, which is instead of one to many, it becomes many to one. And this is where we were facing the most problems. So since realistically this second multicasting socket was functioning as a unicast socket, I changed it. I made it an unicast socket, and I found that there was a slight improvement where I could image 100 nodes. But more than 100 nodes, the NodeHandler was able to support, and so I had to abandon that approach too. I'm going to the next slide now. So what I introduced is, I introduced a multiple multicast socket scheme. So in this scheme, what I did is, for the NodeAgent to NodeHandler communication, for the first time, I divided the NodeAgents into groups. And I opened up 4, instead of a single multicast socket, I opened up 4 multicasting sockets. And each socket in the NodeHandler was taken care of by a thread. A thread would sit here, it would receive messages from this, and it would write the message into a common internal queue from which the request handler thread would process. Once I did this, and I made an interesting observation. What happened is, there was severe race conditions. As you see over here, a shared hash function is getting modified while it's iterated upon by another one. Now what happens is, another observation that I made was,
So there is no serialization, there's no mutex or semaphore, nothing on
No.
shared variables.
no, and once I added that, the performance degraded like anything. So I had to abandon those.
Yeah, of course. Yeah.
So then what happened is, and the interesting thing was, here, if instead of 4 sockets, I have 2 sockets, which is 2 additional threads on the process, then the frequency of this error reduces. But here if I have 6 sockets, then the frequency of this error increases. So this from this case I was able to conclude that this was happening because the process was vastly overloaded. It was a process overload problem, and the NodeHandler of 364, it was able to cope up with the workload in a 64 node grid, but in a 400 node grid it couldn't put up with the workload, and so process overload formed the basis of investigation in phase 2. And this is when I tried, the main focus of investigation in phase 2 was that unburden the process, and for that I needed to make architectural changes.
I need to bring up an issue here. It's already 2:55, and we were supposed to have this limited to about an hour,
Okay.
an hour and 10, 15 minutes.
Yeah.
We just spent about 30 minutes covering phase 1, and there are 2 more phases.
Those are not so big.
Right, so just be aware of my time constraint,
Yeah, okay, yeah.
because I have to go to campus soon.
Yeah. So now this is the phase 2 where the architectural changes were done. I have changed the slide to phase 2. The first was, as I had discussed with you, the multicast clients, the 4 client processes that I had introduced, where each client handled a group of 100 node agents. The node agents, instead of directly sending message to the node handler, send message to the client process, and the client processes filtered the messages before sending it to the node agent to the message queue. So because of this change, I had to make slight changes to the node agent communication layer too. For the node agent to node handler communication layer, this node agent was changed. For node agent was changed to communicate with the client process. And for the node handler to node agent communication, which is the other way, since there were 4 sockets, the node agent had to identify the socket to which it would bind. Similarly, these intervals were increased to reduce the traffic, like reduce the frequency of the heartbeat messages and the handler timeout checking by the node agent. Similarly, correspondingly, I had to make some changes to the node handler, which is what, instead of waiting on the socket, it would wait on the message queue. Of this, as I said earlier, 4 sockets were opened up. And now regarding sending messages through the 4 sockets to the node agents, the messages being sent were grouped, like the hello, the load image, and the recent messages were sent to all node agents. But the retry and the alias message were sent only to specific group of node agents, which meant that a node agent in group A reports that a message has been missed. So the retry would be sent only to that group and not to all the remaining 3 groups. And last was the message queue that was introduced. Here I am using the sysvipc Ruby library for that. The other thing that I made was I ran the Ruby profiler to find out where the maximum amount of processing was taking place. I found that this particular call was taking 19.36% of the time, and after this was removed, the maximum time was taken up by the REXML calls. So this function, the datetime class which invoked this, I replaced it with time.strf time. This is 800 times faster than this, though it performs the same function. Similarly, all REXML calls were removed. The last change that I made was XML tree parsing. I removed the XML tree parsing entirely, and whatever node status information is needed, I am just storing them into local variables. And also, whatever XML information was getting written to a log file, I have disabled that entirely. So this is the example of the XML tree that is constructed. As you see, for each node, it shows the .OK message has come, and it shows the progress. Now in step 2, in phase 2, these are the steps. First, I set up the communication layer, like the 4 client processes, and the node agents were configured to communicate with this. And I found that when I tested those, I found that all 400 node agents could communicate with the client processes simultaneously. At this stage, I had just introduced NodeAgent and the clients. I didn't introduce the message queue side. Once I had tested this out, I introduced the remaining sections, which is the message queue communication. And once I did that, I was able to successfully image 160 nodes. Now when I tried to image more than 160 nodes, I found that the process was under stress. So because of that, that's when I ran the profiler. I ran the profiler, I removed the calls, I made the function call changes, and I was able to image 278 nodes. More than that, again there was process stress. The last stage, when I removed the XML tree parsing, I was able to image 394 nodes. The rest of the nodes I couldn't image because those nodes had hardware problems. So this ended the phase 2, and the version that was developed at this phase is the base experimental version. I am changing the slide to investigation phase 3. So in phase 3, what I did was I mainly concentrated on robustness and optimization. That is, I used the base experimental version because to handle all the error conditions that were being faced in the big grid. One was the node startup error. Some of the nodes would go into an indeterminate state if the sequence of power off, reset, and power on commands were issued in quick succession. So what I did was I removed the reset command and I introduced an interval, a sleep interval between the power off and the power on. Another was node blocked. In this case, what happens is the nodes would come up, the imaging would start. After 60% progress, the node would crash and there would be no communication after that. So I added code to exclude those nodes that from imaging that had not communicated for 600 seconds. Similarly, incorrect booting. Some of the nodes for the big grid were found to repeatedly boot off the local disk instead of the PXE image. So these nodes were excluded after 2 booting attempts. Similarly, the large scale incorrect booting was that majority of the nodes, when they boot off from the local disk, the NodeHandler was found unable to cope up with it. So what it did was, to get rid of this, instead of powering on all the nodes together, I am powering them in groups of 80 now. The other optimization was, initially I had started with 7 multi-class clients because the big grid, the small grid supported 64 nodes, so I used a number 60 as the basis. But after that, when I optimized, I included it to 100 nodes. Similarly, the process threads. I optimized the NodeHandler process not to have 4 threads, but to function with 3 threads. So at the end, and after I optimized the imaging script to the entire imaging process was done with 4 threads as against 9 previously. Similarly, reducing network traffic, all these intervals were increased. And also at the end, what used to happen is the NodeHandler used to switch off the nodes only after all of them have completed imaging. But now what I am doing is, as soon as a node says I have completed imaging, the NodeHandler will switch off that node. So this substantially reduces the heartbeat messages that are sent by the NodeAgent. Similarly, reducing the number of sockets, the optimum number seems to be 4 in each path. And the last was the imaging script that was optimized. So here I am defining the experiments. This is where I am defining the experiment parameters, which is the same as before. The change that I made was here. This is also a defining parameter. Now a single every call handles all that was handled before by an every, a when all, and a when all up. So the imaging script now contributes only 1 additional thread to the NodeHandler. The lessons learned. So based on the entire investigation, the lessons I learned were, in this case what I was doing was, I wasn't designing a system from scratch. There was already substantial user code existing. And so my limitation was that I can't expect the users, each and every user, to go and change their script. So whatever changes I made, I had to make the changes invisible to the users. Second is, I adopted a bottom-up approach. Because the reason is, if I made a top-down approach, what happens is all the problems would come simultaneously and I wouldn't be able to isolate each and every problem. But if I have a bottom-up approach, what happens is I can solve the problems having a local scope. Similarly here, system designers should never allow users to alter the system architecture, which we saw was happening because extra threads were added to the NodeHandler process. A user can just set up a script and call every and have 100 or 200 threads, and that would crash the node handler. The third is that minimizing the number of threads. This is my personal preference. If there are multiple threads that perform the same function, we can have 200 of those, no problems. But if there are multiple threads that perform different functions, it would be better to limit the number of those threads by clubbing together the function of multiple threads. And serializing access variables, this is what should always be done.
Yes, okay. Let me put it on the screen.
I am discussing the lessons learned section now. Another was event triggering. Here in the old version, what was happening was one thread was checking for whether all the nodes are booted up, and another thread was issuing the load image procedure. But what was happening is, in the correct sequence, the checking for the booting should be done before the load image procedure is started, but this was not happening. So what I did was, I combined both these threads into a single thread so that the sequence is maintained. Sixthly, XML as a data structure seems unsuitable because it requires a lot of processing time. Importantly, we need to choose carefully the implementing language. The next, number 8, is when we make a scalable design, we should have a plug-in approach so that we can add components with minimal changes, maybe at most a change to the config file. In this case, to add a new client process, we just need to make a change in the config file, and that would add a new client process to the node handler. The ninth is, when we are designing where we don't know what the problem is, what we are facing in the future, we should always make the choices that we should always choose an option that provides the greatest amount of flexibility. Because if we choose an option that doesn't give us the flexibility, we will be precluding entire field of options that we could have chosen from.
So what is the flexibility here?
See, in this case, if I had chosen pipes instead of message queues, what would have happened? If I choose pipe, I would be limited to just one single communication layer process. And for a pipe, to have multiple communication layer client processes, I would have had to add multiple threads, one for each pipe or two for each pipe. But if I have a message queue, what happens is I can have multiple processes that will read on the same message queue, and I can implement a single reader, multiple writer. But if I use a pipe, I exclude the possibility of having multiple client processes. And the last is, which I have always believed in, is to keep the design simple and free of redundancies. This because afterwards it helps us understand, and if you go to enhance or modify the system, it makes the entire process very easy. The conclusion we can draw is that it was the process overload problem which was the main cause, and once this got rid of, the node handler started working. There's also a possibility that multicast socket communication might be responsible in a minor role, but with whatever I have done, I haven't found anything definite yet. And the future work is, I tested it with image nodes. I need to test it with the other applications like save node, the tutorials. And I would like to also explore this node handler implementation with C++ or C. Thank you.